Sagittarius A. At the center of the Milky Way, 26,000 light-years from Earth, lies Sagittarius A, a supermassive black hole with a mass estimated at 4.3 million suns. Its gravitational field governs the motion of nearby stars, many of which complete orbits lasting between 10 and 20 years. In April 2019, the Event Horizon Telescope, a global array of synchronized radio observatories, captured the first direct image of its shadow, confirming theoretical predictions made decades earlier. Gas clouds near the event horizon move at nearly 30% of the speed of light, producing variable X-ray emissions that fluctuate unpredictably. One event in 2012 drew particular attention when Sagittarius A brightened by a factor of 150 in less than an hour before fading without explanation. Some researchers propose the flare was caused by a fragmenting gas cloud or a disrupted asteroid, but no model fully accounts for the rapid change. Each unexplained outburst keeps astronomers monitoring around the clock, setting the stage for the next mystery. Millisecond bursts of radio energy so powerful they outshine entire galaxies. Fast radio bursts. First detected in 2007 at Australia's Parkes Observatory, fast radio bursts, brief flashes of radio energy lasting mere milliseconds, emit more power than an entire galaxy in that instant. Analysis of their dispersion shows origins between 100 million and 8 billion light-years away, suggesting immense forces compressed into incredibly short timescales. Some fast radio bursts repeat predictably, while others appear only once, implying multiple astrophysical mechanisms rather than a single cause. In 2020, astronomers recorded a burst within our own Milky Way from Magnidar SGR 1935 plus 2154, proving that at least some FRBs arise from highly magnetized neutron stars releasing sudden magnetic stress. The energy output of that single burst equaled the Sun's annual radiation compressed into milliseconds. For astronomers, each new detection acts like a cosmic radar ping through the intergalactic medium, mapping unseen matter between galaxies. Their unpredictable timing drives round-the-clock monitoring efforts. Tabular ice moons. Two of the most studied bodies in the outer solar system, Europa and Enceladus, offer the strongest evidence for liquid oceans beyond Earth. Beneath their frozen crusts, both moons conceal subsurface seas estimated to be 60 to 100 kilometers deep, kept warm by tidal flexing from their parent planets, Jupiter and Saturn. The Cassini spacecraft, during its flybys between 2005 and 2017, detected plumes erupting from Enceladus's south pole, shooting water vapor and ice particles nearly 500 kilometers into space. Detailed spectrometry confirmed the presence of organic molecules, salts, and molecular hydrogen, key ingredients for potential microbial life. Europa shows similar activity through surface fractures known as lineae, where cryovolcanic jets may intermittently vent subsurface water into orbit. NASA's upcoming Europa Clipper mission, launching in 2024 with a mass of roughly 6,000 kilograms, will conduct nearly 50 close flybys to determine whether Europa's ocean could support biology. The data it returns will redefine how astronomers search for life in the solar system. Galactic cannibalism. Across the cosmos, galaxies grow not through peaceful expansion, but through collision and consumption, a process astronomers call galactic cannibalism. The Andromeda Galaxy, located 2.5 million light-years away, is currently devouring smaller companions such as M32 and M110, leaving visible tidal remnants along its spiral arms. Meanwhile, the Milky Way itself is absorbing the Sagittarius dwarf galaxy, whose stars and gas clouds stretch across the sky in looping streams recorded by the European Space Agency's Gaia mission. Data from Gaia's precise stellar mapping, tracking more than 1 billion stars, confirms that these interactions reshape galaxies from the inside out, redistributing dark matter and triggering new waves of star formation. In roughly 4 billion years, Gravitational attraction will pull the Milky Way and Andromeda into a head-on collision lasting several hundred million years, eventually merging into a single elliptical system informally called Milkdromeda. Simulations suggest that while the night sky will flare with billions of colliding stars, our sun and planets may survive the encounter by drifting into a new orbit around the merged core. The long-term evolution of such cosmic mergers reveals how galaxies recycle themselves across epochs, a process that contrasts sharply with another great mystery of the universe, the invisible energy driving them all apart. The Botez Void. Discovered in 1981 during a redshift survey led by astronomer Robert Kirshner, the Botez Void remains one of the most baffling structures in the known universe. Located about 700 million light-years away, it spans roughly 330 million light-years in diameter, large enough to contain thousands of galaxies, yet fewer than 60 have been identified within it. Spectroscopic mapping confirms its near-total emptiness, suggesting an extreme deviation from the expected large-scale structure of the cosmos. Simulations indicate that such a vast void could arise from quantum fluctuations during the early universe, amplified by cosmic inflation to produce regions where matter density dropped close to zero. The discovery challenged assumptions about how uniformly matter was distributed following the Big Bang and forced cosmologists to refine models of galactic clustering. Even today, the Botez Void is nicknamed the Great Nothing, a region so empty that light from one edge would take 330 million years to reach the other. Its very existence raises one final, unsettling question. Why does anything at all fill the darkness, when physics suggests the universe could have remained truly empty? Dark energy. In 1998, two independent teams studying Type Ia supernovae, the Supernova Cosmology Project and the High Z Supernova Search, recorded a discovery that overturned cosmology. The universe's expansion is accelerating. The data showed distant supernovae were dimmer than expected, implying galaxies are moving away faster over time, rather than slowing under gravity. This acceleration requires a force or energy making up roughly 68% of the universe's total energy density, now known as dark energy. The leading explanation treats it as a cosmological constant first proposed by Einstein in 1917, representing a vacuum energy inherent to space itself, though alternative theories suggest a dynamic scalar field that evolves with time. Because dark energy acts uniformly, it counteracts gravitational attraction and drives galaxies apart at an ever-increasing rate. If its strength continues to grow unchecked, the so-called Big Rip scenario predicts a future where even atoms and subatomic particles are torn apart. Understanding this invisible pressure remains one of physics' greatest challenges, and it compels astronomers to measure the cosmic background itself for hidden irregularities, anomalies that might reveal whether our universe is truly uniform or subtly distorted by something deeper. Rogue planets. Astronomers estimate that billions of rogue planets drift through the Milky Way, unbound to any star and moving silently through interstellar space. These planets likely form within young solar systems before being ejected by gravitational interactions with larger worlds or nearby stellar clusters. In 2023, the James Webb Space Telescope recorded dozens of such free-floating objects in the Orion Nebula, including several that appeared as gravitationally bound pairs, essentially twin planets orbiting each other without a parent star. Their discovery challenges long-standing models of planetary formation, which assumed such objects could not remain stable without stellar heat or light. Some theories suggest internal radioactive decay or tidal heating could sustain subsurface oceans beneath thick ice layers, creating isolated environments potentially capable of harboring microbial life. The idea that life could persist on planets wandering the galactic void expands the definition of habitability beyond traditional boundaries. These findings redefine what it means to be a planet at all, setting the stage for another puzzle that began with a single, unexplained signal captured from deep space in 1977. The WOW signal. On August 15, 1977, Ohio State University's Big Ear radio telescope recorded a 72-second burst of narrowband radio energy originating from the constellation Sagittarius. The signal's intensity spiked to 30 times the background noise, fitting perfectly within the frequency range scientists consider optimal for interstellar communication. Astronomer Jerry Amon, reviewing the data days later, famously circled the printout and wrote "Wow" in red ink, giving the event its enduring name. Despite extensive follow-up campaigns using facilities like the Very Large Array and the Green Bank Telescope, the signal has never repeated, defying efforts to identify a natural source. Subsequent hypotheses included passing comets, hydrogen clouds, or terrestrial interference, yet none fully matched the observed frequency drift and strength. Its precision and duration suggest a fixed extraterrestrial origin, but with no recurrence, it remains a single unverified anomaly. The WOW signal stands as one of search for extraterrestrial intelligence's greatest unresolved detections, leading astronomers to re-examine every transient object crossing our solar system. If you enjoyed this, I'm going to be posting a lot here. I would greatly appreciate it if you could subscribe. Thanks for watching.